Okay, chapter 4 starts with 4.1, which is on exponents. So a little review here. Wow, everything's messed up here. Not really sure what this means. Can't see any colors. Anyway, we'll see what color I get here. 5 to the 0 power. So most of the stuff down here in this first section should be review. So what do you know about anything raised to the 0 power? Anything to the 0 power is 1. Doesn't matter if it's 5 to the 0, if it's -2, all to the 0, if it's b to the 0, all of those things equal 1. Right? All right, here we have a product of powers. We're multiplying two powers together. They have the same base. The base is 5, right? So what can we do to the exponents? This should be definite review for you. If you're multiplying, you have the same base, add the exponents, you get 5 to the 6th power. That's simplified. You could then do that if you want. Figure out what 5 times 5 times 5 times 5 times 5 times 5 is. I don't want to do that right now. Okay, if we have the same base, 5 again, and we are dividing. Don't divide the exponents, you subtract them. So you get 5 to the 6. By the way, this also works with negative exponents. If you had 2 to the -3 divided by 2 to the -5, that's the same as 2 to the -3 take away -5. It equals 2 squared, which equals 4. Hey, that was a lot easier than actually changing both of these into fractions and dividing. Okay, so it works whether they're positive or negative. How about this? It's a power of a power. Hard to read this. It's 5 cubed squared. What do you do with the exponents there? You multiply them. So you end up with 5 to the 6th power. All right, this is spreading the love. You have 5 times m squared, all cubed. And if you're multiplying two things, you can spread the love of this power here. This 3 applies to the 5, and it also applies to the m squared. So you get 5 cubed times, if you want, m squared cubed. Okay, well 5 cubed is 5 times 5 times 5, that's 125. And m squared cubed, oh, that's this rule back here. It's the power of a power rule. So we multiply the 2 and the 3, we get m to the 6. So you get 125 m6. Here's another spread the love. When you divide, you can also spread the love. So this 4 applies to the n squared, it applies to the 3, and it applies to the m here. So we get n squared to the 4th power, we get 3 to the 4th power, and we get m to the 4th power. N squared to the 4th power. Oh, that's the power of a power rule again. You multiply. So you get n to the 8th power. 3 to the 4th power is 3 times 3 times 3 times 3. That's 81. And m to the 4th. Can you do this? If it's m plus 2 cubed, can you spread the love? No, you can't spread the love when it's adding. How about if it was subtracting here, m minus 2? No, you can't spread the love. You can't make it m cubed minus 2 cubed. You can't do that. You can only do that when you're multiplying, like in this instance, or dividing, like in this instance. Can't do that. Really wish I could take a different color. I guess I could do it this way, couldn't I? So here we go. We have 5 to the -3. Uh-oh. If you have a negative exponent, remember it's a flippin' negative. Right? We don't like negative exponents, so we say, oh, flip, because we're good people. So flipping negative. All right, so this 5, which is actually 5 over 1, flips to become 1 over 5. And now we've taken care of the negative. We're now just left with 5 cubed. So you get 1 over 5 cubed is 5 times 5 times 5. That's 125. Another flipping negative, so what happens to 2 over 3? It becomes 3 over 2, all in brackets still, but it's not -4 anymore, it's just 4. Hey, which rule do we now follow that we've already looked at up here? This one right here. We have spreading the love. It's a dividing, so you're allowed to spread the love. So you have 3 to the 4th power over 2 to the 4th power. 3 to the 4th power is 81. 2 to the 4th power is 2 times 2 times 2 times 2 is 16. And the last thing here, we haven't actually talked about this before. This is 5 to the a power equals 5 to the b power. What I'm saying, what we need to know here is, if this is true, if 5 to the a power is equal to 5 to the b power, guess what's true? You can probably guess. If this is true, then let's say if this, then a equals b. And this is very, very useful for solving exponential equations. You'll see this just down below a little bit. Okay, let's try simplifying. Oh my goodness, this is the sort of question that gave you fits in grade 10. Let's see how we can do here. So, if you notice, you have three different monomials here, and there's only one of them that's raised to an exponent, and it's a negative exponent. So, there's different ways you could do this. You could multiply this, you could spread the love right here. I think the better way to do it might be to deal with this negative here, this flippin' negative. So where does this flippin' negative, where does it make this whole term end up? It makes it end up flip down into the denominator. So I'm going to do that as my first term. I'm going to keep this first monomial the same, 2x to the negative 1 y squared over, because this part is now flipped into the bottom. So I'll rewrite the 12x squared y squared. But now the 4x squared y to the negative 3 is in the bottom. It's no longer to the negative 2, it's now squared. Okay, the next thing I'd do is deal with that squared, and I would spread the love. So again, I'd like a different color here. What's going on with this today? So I want to spread this 2 here to the 4, the x squared, and the negative 3. So a lot of writing here. This is intolerable. I get 2x to the negative 1 y squared on top. This also stays the same, 12x squared y squared. But now in this new bracket here, I have 4 squared, so let's just write immediately 16. X squared squared, which is x to the 4th, and y to the negative 3 squared. What do I do with the negative 3 and the 2 here? I multiply them, so I get y to the negative 6. Okay, I'll go down here next. Next, I probably want to combine these two monomials in the bottom by multiplying. So I have 2x to the negative 1 y squared on top. I don't have to put in brackets, so I won't. 12 times 16, oh gosh, that's not easy. That's 192. X squared times x to the 4th. Remember, we're going to add the exponents, so we get x to the 6. And y squared times y to the negative 6. 2 plus negative 6 is y to the negative 4. We're almost there. One last step. Here we go. Look at the coefficients out front, the 2 and the 192. If it was 192 on the top and 2 on the bottom, you could just divide it. 192 divided by 2 equals whatever. But you can't divide this, you get a decimal. So what you do is you think of it like a fraction. You think, if I had 2 over 192, what would that be as the lowest term fraction? Well, I could divide them both by 2, so I get 1 over 96. Okay, x to the negative 1 over x to the 6. This is divided, so you could subtract the exponents. Negative 1, take away 6, which is negative 7, but we don't want it to be negative, we want to make it positive, so we flip it into the denominator. Or, the other way I taught you, and the way I like to think of these is, where do you have more x's, in the numerator or the denominator? Well, definitely in the denominator, because 6 is bigger than negative 1. How much more is 6 than negative 1? It's actually 7 more, isn't it? Because it's 6 to get down to 0 and 1 more to get to negative 1, so you have 7 here. Let's do the same thing here. Where do you have more y's, the top or the bottom? Definitely the top, because it's positive in the top, negative in the bottom. How much more is 2 than negative 4? 2 is 6 more than negative 4. We're finished. You actually don't need this 1 here, do you? You could just have y to the 6 equals 90, not y to the 6 over 96x to the 7th. If you have a 1 there, that's totally okay. Okay, next one. Different ways you could do this. Let's start by doing power, spreading the love. Sorry, let's start by spreading the love. So we're going to spread love both these. So you get 3, negative 2x to the 2, so it's power of a power. Negative 2x times 2 is negative 4x, times 9 to the 2x squared, that's power of a power. 2x times 2 is 4x. Can we combine these exponents? No, because we don't have the same base. But we can actually get the same base. How can we get the same base? Make this 9 3 squared. So we have 3 squared to the 4x. Alright, this stays the same, 3 to the negative 4x. That's a negative 4, believe it or not. Times 3 squared to the 4x. We have another power to power, power of a power. 2 to the 4x is 3 to the, multiply those, 8x. Now you have the same base. That's great, because when you multiply and you have the same base, you keep the base the same and you add the exponents. Negative 4x plus 8x is 4x. Now we could look at this. It seems like this is done, doesn't it? But you're not, because you can actually look at this first. This is the same. 3 to the 4x, it's the same as 3 to the 4th to the x. And what is 3 to the 4th? 3 to the 4th is 81. 3 times 3 times 3 times 3 is 81, and you still have to the x power. This is your final answer, 81 to the x power. A little different, isn't it? A little strange. That's the sort of thing we have to tackle this year. What we're going to do now is we're going to figure out how to solve exponential equations. Exponential equation is when you have a variable in the exponent. And for example, if you look at all these equations, there's variables in the exponents. You have an x in the exponent there, an x in the exponent, x in the exponent, x in the exponent. There's all these variables in the exponent. So how do we solve these? Well, there's 3 steps. You're going to write each side of the equation with the same base. You're going to use exponent laws to get only one base on each side of the equation, and then you're going to equate the exponents and solve. So let's try 3 of these. First one, 4 to the x minus 1 equals 2 to the x plus 3. They don't have the same base, but we want them to have the same base. How could you get the same base? 2. The number 2 should be in your head, right? Because 4 is the same as 2 squared, and then we still have that x minus 1. This one we don't have to do anything to. 2 to the x plus 3. Now, do you see you have the same base here? And this is exactly why we taught this rule right here. If you have 2 powers that have the same base, then their exponents must be equal to each other. So in this case, we have 2 powers with the same base. So what that tells us is that the exponents, 2 to the x minus 1, must be equal to this exponent, x plus 3. So that's what we did in step 3 here. Equate the exponents, and now we solve. Oh, we can solve this. Let's do mountains here. 2x minus 2 equals x plus 3. Let's bring the x over and subtract, so you're left with x. And let's move the 2 over and add, so you get x plus 5. Not x plus 5, x equals 5. Sorry. You could check that if you want. You don't have to, but you could check it by plugging into both these spots. You'll see it works. All right, next one. We need to get the same base, 9 and 27. Oh. What's a number that we could raise to different powers and get these numbers? 3. 9 is the same as 3 squared, and we have that x, so 3 to the 2x equals the square root of 3 cubed. Now, this isn't good yet because we still have this square root sign. So here's one last step, which I should have put up here. Uh-oh, kind of annoyed with myself now. Do you remember what a fractional exponent means? So for example, if we have 16 to the 1/2, that's the same as the square root of 16, which is 4. How about 27 to the 1/3? That's the same as the cube root. That 3 is the root. Remember, it's underground, so it becomes the root. The cube root of 27, which is 3. And one more. How about 16 to the 3/4? Okay, the number on the bottom is the root. That comes out front, so you get a 4. Base is in there. And this 3, you can put it either around the whole thing, or you could put it right with the 16. It's usually easier if you put it outside the whole thing, because we want to do the fourth root first. The fourth root of 16 is 2, because 2 times 2 times 2 times 2 is 16, and then we raise it to the 3rd power, we get 8. Okay, quick review of those. So if we have this square root sign there, what's that the same as? That's the same as 3 to the 2x power equals 3 to the 3rd, and we're taking the square root of all that. What's another way of saying square root? Right here, 1/2, right? The square root's the same as raising it to the 1/2 power. So we have 3 to the 2x equals, hey, here's power of a power. 3 times 1/2 is 3/2. Now we have the same base, and we have these 2 powers equal each other, which means the exponents must be equal to each other. 2 to 2x must be equal to 3 over 2. Last step, divide both sides by 2. So you get x equals 3 over 2 divided by 2, which is the same as 3 over 2 times 1 over 2. You get 3 over 4. Okay, last one. Square root of 7 to the x plus 1 equals cube root of 49. The number 7 should pop in your head. You can get both of these to be base of 7. So the first one, you have 7. Square root of that means raised to the 1/2. And all of that is raised to the x plus 1. And here you have 7 squared, that's what 49 is. and then we want the cube root of that, and cube root is the same as 1/3, isn't it? Okay, let's keep the bases for now. So we have 7 to the 1/2 to the x plus 1. This is power over power. We're going 1/2 times x plus 1. I guess I could have done that, but I'll just write it like that. And here you're going power over power. You're going 7 to the 2/3. I'll do that in one step. Okay, we got the same base, so we can make the exponents equal to each other. So as I do that, let's also do the mountains right here. Right there, because we're multiplying that. So we get 1/2 times x is 1/2 x. 1/2 times 1 is 1/2, and that equals 2/3. Might want to get rid of those fractions by multiplying by the lowest common denominator, which is 6. We'll multiply this by 6, this by 6, and this by 6. We multiply this by 6, you divide first, you're left with 3, and 3 times 1 is 3. When you multiply this by 6, you divide first, you get 3, and 3 times 1 is 3. Oh, sorry, this should be 3x, plus when you divide this one, you also get 3. And when you divide this one, you get 6 divided by 3, which is 2. Multiplied by this 2, you get 4. Now we just solve this. Take away 3 from each side, so you get 3x equals 1. Divide by 3, x equals 1 over 3. Okay, the last thing today is exponential functions. These are functions that look something like of this form. Y equals b to the x power. And there's two restrictions here. B has to be greater than 0, and b can also not equal 1. Now, this is a new mother function we need to graph, y equals b of x, but the b could be different numbers. You know, it could be, as we said, anything as long as it's greater than 0 and not equal to 1. Let's do probably the easiest one, I suppose. Let's do when b equals 2. So we're going to graph y equals 2 to the x. And as we always do, we're going to squish it in here. The first time we graph something, we usually do table values, and I like to go from -3 up to 3. Whoops, as I cross out the numbers I just wrote, -1. Okay, 2 to the -3. Well, 2 to the -3, 2 to the -3, that's a flippin' negative, so it's 1 over 2 cubed, and 2 cubed is 8, so you get 1 over 8. 2 to the -2 is also a flippin' negative, so you get 1 over 2 squared is 1 over 4. 2 to the -1 is also a flippin' negative, you get 1 over 2 to the 1, or just 1 over 2. 2 to the 0, anything to the 0 power is 1. 2 to the 1 is 2. 2 squared is 4, and 2 cubed is 8. Let's graph these points. -3 and 1/8, very low here. -2 and 1/4. -1 and 1/2. Whoops, that's not quite a half, but you get the idea. 0, 1, 1, 2, 2, 4, and 3, 8. Now, if these numbers got lower and lower and lower, -4, -5, -6, do you see what's going to happen? You're going to keep flipping it, so it's going to be 1 over a bigger and bigger number. In other words, it's going to get closer and closer to 0. Hey, what does that sound like this shows up here? What kind of line? If it gets closer and closer and closer to something, there must be an asymptote. And there is. There's an asymptote right here. I guess we could draw it in. There's an asymptote right here at the x-axis. Now there's two very, very important points here. No matter what this number is here, whether it's 2 or 4 or anything, 17,000, when you raise it to the 0 power, what do you get? 1. So this point here, this 0, 1, is always going to be there. It's always going to go through the point 0, 1. Now, regardless of what value you put in here, so if I call this y equals bx like I did here, if you put 1 there, you get b to the 1 power, which is b. If you put 1 here, you get 2 to the 1 power, which is 2. If you put 7 to the x and I put if it's y equals 7 to the x and I put a 1 there, you get 7 to the 1, which is 7. So you're always going to go through the point 1, b. So these are 2 points that always show up. You'll always have the point 0, 1, and you'll always have the point 1b. b being the base, right? Whatever the base is here. So I wrote this for you. It always will pass through 0, 1. It always passes through 1b. And the last point I made for you, the last point I made for you is that there's a horizontal asymptote at the x-axis, which is y equals 0. That's the equation of that, right? Okay. Now, what if, so we've looked at a case where the base is bigger than 1. What if it's less than 1? I mean, we said it has to be bigger than 0, but it could also be between 0 and 1. Like, what if we had something like y equals 1 half x? 1 half, sorry, to the x power. Well, again, let's do our table. X, y, negative 3, negative 2, negative 1, 0, 1, 2, 3. 1 half to the negative 3. Oh, that sounds like another flipping thing. So that's the same if we flip this 2. 1 half, we get 2 cubed, which is 8. If we put 1 half to the negative 2, you'd flip it, you'd get 2 squared, you get 4. If this is negative 1, you flip it, you just get 2. Anything to 0 power is 1. 1 half to the first power is 1 half. 1 half squared is 1 quarter, and this is 1/8. Do you see it's just exactly the opposite here? And that shouldn't surprise us too much. I'll graph this first, and then we'll talk about that. Negative 3, 8. Negative 2, 4. Negative 1, 2. 0, 1. 1, 1 half. 2, a quarter. And 3, 1/8. You can see again that we have a horizontal asymptote at the x-axis. You can see again that this graph goes through the point 0, 1, as we said it always would, unless you have other transformations. And we see again that it goes through the point 1, b, right? What's b in this case? b is 1 half, and that's where it goes through, 1b. And this point here is 0, 1. Now, if you compare this graph over here and this graph over here, what's the relationship between them? It's a reflection over the y-axis, and that's exactly what we would expect, because this graph right here is exactly the same as y equals 2 to the negative x, right? If this negative is a flipping negative and would flip it to 1 over 2, and then it would be positive x. If you compare this equation here, y equals 2x, and this equation here, y, I guess this should be like an arrow, y equals 2 to the negative x, you can see the only difference is this negative here. What does a negative in the function do? If it's a negative in the function like this, it reflects the graph over the y-axis, and that's exactly what happened here. So it's not surprising that happened. Okay, let's quickly graph a couple of them here using transformations if we can. So the first one we're going to do is y equals negative 3 to the x power plus 1, and the second one we'll do is y equals 1 half to the x minus 2 take away 2. Let's do the second one first because it's very quick. We've already drawn basically y equals 1 half x. What's the only thing difference between that graph and this graph? Y equals 1 half x minus 2 minus 2. Well, this is a negative 2 in the function, so that's a horizontal shift to the right. So we have to go 2 steps to the right. And then this is a minus 2 outside the function. That means we're also going 2 down. So all we have to do is take some of these points and move them 2 to the right, 2 down. Well, I guess the most obvious points to move would be these ones. So 0, 1 would go 2 over, 2 down. And 1b, which was at 1, 1 half, would go 2 over and 2 down. And the horizontal asymptote, which was at the x-axis, moving the asymptote over does nothing, but you would move it down, so it would now be 2 down, so your horizontal asymptote will now be right here. And you're now pretty close to being ready to graph this thing. You know that this thing's going to get closer and closer to the asymptote here, and maybe you want to see, well, where's the y intercept? Where does this go through? So you could put one point in here. You could also move more points from up here if you wanted. Like, I don't know, let's move this point. Negative 2, 4 is going to go 2 over and 2 down. Oh, there you go. It says 0, 2. So you know it goes here. But let's say you didn't want to do that. You could also plug points in. You can always do that, right? You can always use table value. So you could put 0 in here. You get 1 half. 0 take away 2 is negative 2, and then minus 2. That's a flipping negative, so you end up with 2 squared minus 2. 4 minus 2 is 2. Yep, that's where it ends up. Anyway, you could do a bunch more points if you want, either by putting them into the table here or by just moving points here, and you'll end up with a graph that looks something like that. I haven't drawn it very well. Okay, this one here, what's this negative going to do? Basically, it's going to take this mother function graph, it's going to flip it over the x-axis, because that's a negative outside the function, and then you're going to have to move it one up. Is it doing anything horizontally? No, you're not doing any reflections. Or so these points here, this 0, 1, and this 1b, let's just write those points down. 0, 1, let's figure out where that moves to. And 1b, well, what's b in this case? B is 3. So 1, 3. Let's figure out what happens to those points. You can see the x value, nothing happens. You're not doing any reflection, there's no negative in there, and you're not translating it because there's no plus or minus. So the x values are going to stay the same, 0 and 1. But in terms of the y, you're going to have to reflect, so it's going to become negative. So 1's going to the negative 1, and then add 1. Negative 1 plus 1 is 0. Oh, it actually goes through 0, 0. This one, you have to make it negative, negative 3, add 1, negative 2. The asymptote was at y equals 0. Now you have to make it negative. Well, negative 0 is still 0, and add 1. So the asymptote is going to be at plus 1. Okay. And we have a point at 0, 1. Whoops. Sorry. We have a point at 0, 0. And we have a point at 1, negative 2. And you can probably see, as we said, we were reflecting this one, so it should stay close to the asymptote here and then move away from it here. So it should go something like this. And if you want, you could do one more point maybe. Maybe you want to know what happens when you put 2 in there. 3 squared is 9. Negative 9 plus 1 is negative 8. You get something like this. Should go through there. Okay, those are exponential functions. Yet another mother function sort of graph that you have to remember, and then you'll do all sorts of transformations, reflecting and translating it. Hope you're not getting tired of that yet. All right, that's it.
Would you walk that walk? Talk that talk and whisper in my ear, tell me that you love me. I love that talk. When you talk like that, you knock me out right off of my feet. Whoa, whoa, whoa.